All right, folks, here we go. This is section 2.4 about rational functions. We'll talk about what those are in a minute. Okay, let's see. I changed the learning objectives compared to the book for this one again, just to try to streamline things. I think it's still a good idea to read the book and get a deeper perspective. And just in general, I think of math like you're learning a language. You want to try to get as many resources, as many you want to get it from as many angles as possible. Different teachers, different texts, different stuff. That way you're immersing yourself and you'll pick it up faster. So anyway, by the end of today, here's what we should do. You should know how to define a rational function. You should know what it is anyway, and understand how to find vertical asymptotes. Along the way, also how to find removable discontinuities or holes. Okay, that's the plan for the first video right now. Things don't always go as planned, as you guys know, but that is the initial plan anyway. And then the second video, we're going to look at horizontal asymptotes and how to find them. And then in the last two videos, we're going to focus on graphing. So, for sure, you're going to see some kind of thing about graphing polynomials and graphing rational functions on the next exam. So that's something to pay close attention to. Graphing rational functions and also graphing rational functions with oblique asymptotes we'll look at as a final topic. Okay, so last two videos, we'll focus on the graph parts. The plan is to do 4. Last time we planned to do 4, ended with 5, so sometimes that also happens. But anyways, let's jump into what's a rational function. A rational function, simply put, is a ratio of polynomials, and it's kind of gives it away right in the word ratio. So it's a ratio. Ratio is just a word for fraction, right, of polynomials. Polynomial on top, polynomial at the bottom, and of course the bottom polynomial cannot be the zero polynomial, because then you wouldn't have something defined. It wouldn't make sense, right? And note also that the rational functions include all the polynomial functions, because q of x, the bottom polynomial, it could just be 1. One is a very simple type of polynomial function, actually, right? It's kind of like a trivial polynomial, but still polynomial. And so you get all the polynomials as, you could consider them as a sort of rational function. It's very akin to the way that we see rational numbers, because rational numbers, a set of those includes all the integers, right? And what's a rational number? Rational number is just a fraction of integers, where you have integer on the top, integer on the bottom. So this is kind of the little connection here to think about it, what I just mentioned, right? Rational functions are to polynomials as rational numbers are to integers. It's kind of like when you took SATs, you got those analogies, right? Bear is to human as dog food is to, or dog is to dog food. Okay, anyway, so that's the connection here. That's the analogous thing. And one more note, anywhere that the q of x, so the denominator, is 0, that represents a domain restriction, because then you'd be dividing by 0, and we all know you cannot do that, right? Okay, let's move right on to vertical asymptotes before we try any questions. So vertical asymptotes, if there are any, they occur when your rational function is in lowest terms, and then after you put in, so it has to be in lowest terms. Once it's in lowest terms, if you notice any values for x that make the denominator 0, then you have yourself a vertical asymptote. We abbreviate vertical asymptote sometimes by VA, not to be considered with not to be confused with the Veterans Association. Notation of vertical asymptotes are vertical lines, and since they're vertical lines, they have the equation of vertical lines, which you've seen before, but that's just x equal to a number. And remember, it's a little counterintuitive. X equals a number is a vertical line, because all the x values are the same on a vertical line. Okay, next idea. Sometimes it looks like there's a vertical asymptote when you just look at the function itself, like not the graph of it, but just the function. Like something like this. Like it looks like there should be an x. It should be a vertical asymptote at x equal to 1, it looks like, right? Because that would make the 0, the denominator 0 would be 0 at x equal to 1, right? But in this case, it's what we call a removable discontinuity, because if you were to put this into lowest terms, then these guys would actually cancel each other out, right? And then you wouldn't have that. When it's in lowest terms, it doesn't have that x minus 1 factor anymore. That guy's gone, actually. And you just have the x plus 2, or some other factors maybe. But it's still domain restriction, because x still can't be that number. But everywhere else, it behaves, this function behaves just like 1 over x plus 2. And so it kind of looks like this. Like you have your graph going along, right? And right at where that discontinuity is, you just get a little hole, and then it continues on as if nothing happened. So it's not an asymptote. When you have an asymptote, what happens is you got a vertical line as an asymptote, right? And then your graph is either going to approach it and go down towards that asymptote, get closer and closer to it, or it's going to approach it and go up. At least it has to do one of those things from at least one side or the other. But typically what happens is it'll go up or down on one side, and up or down on the other side. It could go opposites like this. Here's the same, or they could go opposite like this. And it just depends whether you're positive or negative. Okay, a little bit about notation. And this is kind of it's kind of a topic that you'll see again if you go into calculus later, but it's kind of like the idea of a limit. You're going to get closer and closer to a number. So as x, this right here means x is getting closer and closer to whatever the a value is from the left side of a. It doesn't mean that you're negative. It just means that you're approaching that a value from the left. Like if a is 5, then think of it as like x is going to 4.5, then 4.6, and 4.7, 4.8, 4.9, 4.99, 4.999, It's getting closer and closer to that value, but from the left. Whereas here, x is approaching that value from the right. So if a is 5, again, this would be like 5.1, and then 5.05, then 5.01, 5.001, 5.00001. It's getting closer and closer to 5, but from a little bit above, from the right side of it. Now, if it's a vertical asymptote, that means as you approach that value, then your function either goes to infinity, explodes upwards, or it explodes downwards. And similarly, when you approach it from the right side, either goes to positive infinity or negative infinity. I forgot to add in the negative when I wrote it, so I'm going to fix the notes before I give them to you guys, but for now I just wrote it in with a little red pen. Okay, so yeah, that's all it means. You can reread that later on your own time until it makes sense to you. If my explanation didn't make sense, just take your time and read it, and maybe also, like I said, look up other resources to try to solidify your knowledge. This is asymptotes we're talking about here. Yeah, the same stuff is in the book too. Okay, questions 1 through 5. Let's go on to the questions. This is where I think our understanding really starts to become more solid. And also, when you guys have like a test or something or homework or something, you're doing questions like this, right? So this is the kind of thing that you're expected to know how to reproduce. Oh, okay, so I have my work here because I had to reshoot it. I had a little mistake, so I'm reshooting the video. Okay, find vertical asymptotes or removable discontinuities. Starting with number 1. F of x equals to 1 over x squared minus 4. But x squared minus 4, you should notice that's the difference of squares. That actually factors to x plus 2, x minus 2. So here, this thing is in lowest terms because there's no factors that will cancel, right? So that's in lowest terms. And that means we have 2 vertical asymptotes where the x values will make that 0. So vertical asymptotes, remember, are equations of lines that are vertical, which means they're x equal to negative 2. That's the vertical line at negative 2. And x equals to positive 2. It's vertical line at positive 2. Negative 2 is what makes this factor 0. Positive 2 is what makes that factor 0. Yeah? Okay, so we stated the vertical asymptotes, and now the domain. The domain basically is everything except for x equal to negative 2 or x equal to 2. So basically, you can say it like this. X is not equal to negative 2 and x is not equal to positive 2. Or in interval notation, you can say everything except once you hit negative 2, you stop for a second, and then you start up again, stop again at 2, start up again, and then go onwards toward infinity. Okay, 2 ways to say the same thing for domain. That was number 1. Okay, number 2. Number 2, I planned ahead and I went ahead and graphed it, so I'll show you the graph after this on Desmos. But first, let's just do the question. So what you should notice here, guys, is you have x minus 1 as a factor here, right? But you also have x minus 1 as a factor down here, which means you could essentially cancel them out and say that f of x is equal to, if you cancel that, you get 1 over x plus 1 squared. But you have to be careful here. This is only as long as x is not equal to 1, because if it is equal to 1, then you're dividing by 0, and it's undefined, right? So this function right here is exactly the same as this, except for when x is equal to 1. And it behaves just like this, except for when x equal to 1. Okay, now what are the vertical asymptotes? Let's start with that. Vertical asymptotes, so this thing is the reduced version. So I can look at that to get my vertical asymptotes as x equal to 0 and x equal to negative 1. Okay, those are the vertical asymptotes. Now I have a hole. A hole came from where before I reduced, where I had this factor here. And the hole then is, or we call it a removable discontinuity. Removable because it's removable. Discontinuity because your graph is continuous if you don't have to lift your pencil, but it's a hole. So to make a hole, you have to lift your pencil for a second and then continue on. So it's discontinuous. You broke the continuity. So removable discontinuity so the x value would be 1, right? And what about the y value? Well, the y value is going to be pretty much the y value for this function if it's as if it was this function after you reduced it. So the y value will be what you get if you plug in 1 to this function. So what am I going to get? I'm going to get 1 over x times x plus 1 squared, but I'm going to plug in 1 because that's the value of x that gives me the discontinuity, which is 1 over 1 times 1 plus 1 is 2 squared, which is 1 over 4. So the rest of the discontinuity coordinate is 1/4. Okay, so I said I had the graph prepared. So here it is. Here's that same function right there. Here's what it looks like. You notice that, here, let me write the equations for the two asymptotes. It was at 0, right? It was 1. So you see how that vertical line, this red line, it just splits the graph. The graph is getting closer and closer from the right side. It's going towards infinity. And on the left side, as you approach it from the left, it's going towards negative infinity. The other asymptote was equal to x equal to -1. And see the same kind of thing. The graph is getting closer and closer to that line. And in this case, both of them are going down towards negative infinity. So thinking back to my notation, that would mean as x approaches -1 from the left, f of x is going to negative infinity. As it approaches from the right, it's going to negative infinity. What about 0? As you approach 0 from the left, it's going to negative infinity, but as you approach 0 from the right, it's going to positive infinity. Okay, what about that hole? We had a hole at 1 comma a quarter, right? And if you look at this graph, you can't even see it because it's so tiny. But if I just put my pen over there, watch what happens. So I'm getting closer and closer to that discontinuity, right? 1 comma quarter or 1 comma 0.25. Right at that spot, you see it's undefined. Catch it right there. 1 comma undefined, right? So right there, that's where the hole occurs. Right at 1, it would have been 1 1/4, 1 comma 1/4, but because you can't divide by 0, it's undefined at that one spot. But otherwise, it continues on. It's called removable because if you were just to say, okay, let's define the function to be equal to a quarter at that one spot, then now all of a sudden your line would be continuous. So you could remove that hole by just saying, okay, why don't we just fill it in? And then if you do that, then you've essentially removed the discontinuity, right? You couldn't do that with a vertical asymptote. Those are not removable because how are you going to nail down a spot? How are you going to nail down a single point to fill it in? There's no single position that you could choose. Okay, anyway, let's move on to number 3. So I've got x minus 3 in the top, and the whole deal with these guys is you just got to factor. And this is just by experience. I know it's going to be x minus 3 for one of them. Actually, I don't know that, but I'm guessing because I'm guessing it's going to cancel it down. And what makes 12? 3 times 4 makes 12, and -3 plus -4 makes -7. So that all checks out. Okay, now these guys would cancel, right? So you get 1 over x minus 4. So your f of x is equal to 1 over x minus 4, but as long as x is not equal to 3, because then you'd have a discontinuity lost here, right? So it behaves just like 1 over x minus 4, except when x is equal to 3. Okay, let's answer the rest of our questions. Vertical asymptote at x equal to 4. Let's call it RD for removable discontinuity. That's going to be at 3, comma, whatever the result of that would be at 3. So let's fill that in. 1 over 3 minus 4 would be 1 over -1, which is -1. So -1. Okay, 3 comma -1 is the removable discontinuity location. And then finally, the domain. Domain is everything except for those 2 points, 3 and 4. So x cannot be 3 and x cannot be 4. Or if you like, you can do it this way. Oh, sorry. Positive 3. You can write it the same answer as integrals. Okay, we're going to do questions 4 and 5, and then this video is done. Okay, for next two problems, complete the statements. As x approaches 5 from the left, what does f of x become? And as x approaches 5 from the right, what does f of x become? Okay, so, first thing to notice, okay, let's look at number 4. First thing to notice is if x is equal to 5, exactly equal to 5, then here, that would be 25 minus 25, which is 0, right? So you're undefined. And moreover, let's try to see if we can reduce this any further. So 2x squared plus 1 over x squared minus 25. I could factor the bottom and say that's x plus 5, x minus 5, right? But the top, I'm kind of stuck with that because there's not much you can do with that. There's no number that's gonna make that equal to 0. It just is what it is. So that means it's already reduced. So these two things are vertical asymptotes. Yeah. So in particular, 5, which is the number in question here, because I'm approaching 5 either from the left or from the right. So 5 is a vertical asymptote. So now all I need to ask myself is what's going to happen? Is it going to go towards negative infinity or positive infinity? So let's think here. If I'm going to just look at the signs for these. If x is slightly smaller than 5, so over here, this guy is going to be a positive number, right? Okay, if x is slightly smaller than 5, so I'm approaching from the left, this is going to be something smaller than 5 plus 5. That's going to be a positive number too. And over here, if this is something smaller than 5, like 4.9 minus 5, this is going to be a negative number. So I have something positive on the top and something negative in the bottom, and this negative thing on the bottom is getting closer and closer to 0. But when you divide by something that's smaller and smaller, then you actually get bigger and bigger, right? If you don't believe me, try just divide something on your own. So let's do an experiment. 1 divided by 0.1. That's 10, right? 1 divided by 0.001, that's 1,000. So the smaller number you divide by, the larger the overall number gets. And that's what's happening here. As you get closer and closer to 5, x gets closer and closer to 5, this guy's getting closer and closer to 0. Sorry, I meant this guy. That guy's getting closer and closer to 0. So as he gets closer and closer to 0, this whole thing is becoming, this whole fraction is becoming closer and closer to infinity. Now, because this is positive, and that's going to be negative, this is going to go towards negative infinity. Negative infinity. I don't know why I circled down. So let's complete the statement. As x goes to 5 from the left side, f of x goes to negative infinity. You can also try graphing it to see what happens, and that's another option. But we'll get to graphing later in this section. Okay, okay, now we got to check it from the right side. So as x approaches 5 from the right side, what happens? Okay, so now let's redo this. This is actually a different color, so we can coordinate here. So that was, the red was for approaching 5 from the left side, right? Okay, now as you approach 5 from the right side, this guy is going to be positive. Something close to 5, square it, either way it's going to be positive. This is something close to 5, about 5 plus 5 is about 10. That's going to be still positive. If this is something bigger than 5, like 5.1 minus 5, that's going to be positive now. So all together, everything is going to be positive, which means as x approaches 5 from the right side, and f of x is going to approach positive infinity. It's going to be positive, and it's going to get something bigger and bigger. Yeah. Honestly, this whole concept to me is like something that you would talk about in a calculus class. So you're kind of getting a little preview of calculus here. Okay, that's 4. One more, and this video is done. Okay, number 5. Sorry, guys. I'm not sure if you can hear my stomach rumbling there. Okay, this is negative. Let me just copy this. Negative x squared plus 5x. I'm gonna go ahead and factor here, guys. So I'm gonna take out x. Actually, let me take out a negative x. Okay. So that'll leave me with x minus 5. See that? So that negative x times x is negative x squared, right? Negative x times negative 5 is going to be positive 5x. Okay, and the bottom I've got x minus 5. Okay. I think. Don't want it like this. Okay, I see. So okay, this case, essentially these guys cancel out, right? These guys cancel. So what are you left with? You're left with just negative x, as long as for x, not equal to 5. So what does this all mean? Well, this means your function behaves just like a simple negative x, as long as x is not equal to 5. If x is equal to 5, you have a removable discontinuity, right? You've got a hole. So I can actually graph this whole thing for you real quick, easy. because the graph is just the graph of negative x. Essentially, right? What is negative x? Okay, negative x crosses right through the origin. It looks like a slanted line like this, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's the point right there, right? Okay, so this function here behaves just like negative x, except I have a discontinuity when x is 5. When x is 5, what does that mean? What happens? You just have a little hole right there. So you got this little hole. But otherwise, what would it have been? As you approach this 5 from the left, it's getting closer and closer to the value of whatever negative x was. As you approach it from the right, again, still approaching the value of whatever negative x is. And at that point, if it was filled in, that would have been 5, negative 5. This is what we call a removable discontinuity, right? If you plug in 5 for x, again, negative 5. So 5, 5 is the point at this removable discontinuity, which means I can answer these questions out. As x approaches 5 from the left, what is f of x getting closer to? It's getting closer to negative 5. What about as you approach it from the right? Well, it's actually the same thing, because you're just approaching that hole. As you approach 5 from the right, f of x is also approaching negative 5 still. So that's it. Okay, guys, done with this first video.